Welcome, friends. We first begin with the design principles of refrigeration because that would ground you to the actual design of the refrigeration systems, which we are going to do in the course. We need to understand that we need to be very clear about the fundamentals if you want to design the refrigeration system. We need to understand some very basic principles of heat transfer because that is a core in the design of heat exchanger, core principles of heat exchanger design. We all know that the foundation of refrigeration is basically removal of heat. What we call it as refrigeration is basically we are removing the heat, and this removal of heat or the mode of heat transfer could be by conduction, could be by convection, or could be by radiation. Fundamentally, the major mode of heat transfer in this refrigeration system is conduction and convection. Radiation has not much role to play. We also need to understand that the process of heat transfer, which is happening in the evaporator section of the refrigeration system, is mainly by phase change or evaporation. And you know that basically evaporation is conversion of the liquid refrigeration to the gas refrigerant, right? When you are talking for the refrigeration cycle, liquid to gas. And condensation is just the opposite. Just the opposite means your gas gets converted to liquid, that becomes your condensation. So applying the basic concepts of heat transfer is critical in your refrigeration design. We would be sticking to the very conventional cycle of refrigeration analysis, which is called as the vapor compression refrigeration cycle. Okay, and we would be sticking to the systems which use the compressor. We are not going to talk about the systems like vapor absorption systems or some other non-conventional refrigeration systems. Our focus is the refrigeration system which uses the compressor, that is the mechanical refrigeration systems or vapor compression refrigeration systems, which would be the fundamental systems for our design. So then all our commercial systems would have two heat exchangers, namely the evaporator and the condenser, and two devices which would change the pressure. Compressor would increase the pressure and the expansion device would reduce the pressure. Okay, so in the design of the refrigeration system, we would be basically designing the evaporator, we would be designing the condenser, we would be designing the compressor and the expansion device like capillary tube. Okay, so this you need to understand. When you are talking about design of refrigeration systems, we are basically going to talk about these four components. Okay, and the core of the design is the evaporator must remove the cooling load, that is, and the compressor must match the evaporator and condenser duty. Duty means the amount of heat to be removed or the amount of heat to be added, that is called as duty. So in the design of the refrigeration system, we would be talking about which refrigerant to use, which refrigerant would be suitable for the systems which we are going to design, right? And that selection of the refrigerant would be on the different parameters or different properties. One is the thermodynamic property, other is the chemical property, and then there are some environmental issues which also needs to be kept in mind while selecting the refrigerant. Okay, so this is also to be understood that in the design of the refrigeration system, our selection of refrigerant is also going to play a key role, and the common refrigerants which we will be dealing with in your medical refrigeration systems would be R134A, then R600A, which is isobutane, and R290. And you see that we would be considering the thermodynamic properties, the chemical properties, and the environmental properties for selecting the appropriate refrigerant, which becomes an important part in the design of refrigeration system. We also need to understand a very fundamental relationship between the temperature and pressure, right, while choosing a refrigerant. And we also need to understand the pressure enthalpy diagram of the refrigerant while designing the refrigeration system. Okay, so as all of you know, that basically the temperature, or more correctly the saturation temperature or boiling temperature, is a function of pressure. And what we do in the refrigeration cycle is we boil the refrigerant in the evaporator at lower pressure, and the same refrigerant we are going to condense at the high pressure. Okay, so at low pressure, what we are supposed to do is that we are supposed to evaporate or boil the refrigerant at a low temperature, and at the high temperature, high pressure, the same refrigerant is going to condense. Okay, so this is your cycle, and this understanding is core or fundamental understanding in the design of your refrigeration system. That is the relationship between saturation temperature and pressure. If you go on increasing the pressure, the saturation temperature increases. And in the speciality of refrigeration system is that we need to change the pressure from liquid to gas at lower pressure, and we need to condense this gas back to liquid at a higher pressure. Okay, or in other words, we need to evaporate the liquid at lower pressure in the evaporator, and we need to condense the liquid back to condense the gas back to liquid at a higher pressure in the condenser. Okay, and typically the refrigerant should have a very low boiling point. For example, if you consider R134A as a refrigerant, you'll find that it boils at 0 degree centigrade, okay, when you keep a pressure of 1.9 bar. Okay, and it condenses at 45 degree centigrade, and for that you need to maintain a pressure of around 12 bar. Okay, so about 2 bar pressure you need to maintain if you want to maintain a temperature of 0 degree centigrade in the evaporator, and you need to maintain a pressure of around 12 bar, or more correctly 11.5 bar, if you want to condense the same refrigerant at 45 degrees centigrade. And this, you understand that basically this ratio, that is the condenser pressure upon the evaporator pressure, is critical in the design of refrigeration system. This should not be too large. Okay, and for that, proper understanding of the relationship between temperature and pressure is essential in the design of refrigeration system. The third important part which we are going to cover in the design lectures is the heat load calculations, or also called as cooling load calculations. So basically, we would be focusing on what are the loads, or how much is the heat being added to the system, and by what method this heat is being added, so that if you can correctly calculate how much is the heat being added in the refrigeration system, we can remove it. Okay, so the total load in your medical refrigeration system is because of the product, right? Then because of the transmission, because of the infiltration, and because of the internal heat gain. Okay, so we would be calculating those internal loads, internal heat loads, and the external loads in your heat load calculations part in detail in our next lecture. When you talk about design, we need to understand that basically uh, in the design of refrigeration system, we need to design the evaporator with these four important things in mind. Compressor, we have to design with these three things in mind. Condenser, these three things are important, and in expansion device you need to take care of this too. So what are those things? So in the evaporator, we need to make sure that, because we are talking about a low capacity refrigeration system, we need to make sure that there is a proper contact of air with the surface of the evaporator coil. Okay, evaporator coil design. Then if it is a fin kind of evaporator, there has to be a proper fin spacing, and it is basically denoted by FPI, which is fins per inch. Okay, which is normally stated to the vendor as to how much FPI we are aiming for. There has to be enough surface area, because that is going to matter a lot. in the design of evaporator, and the distribution also should be proper so that the air content is also proper. Okay, so these are the four things you have to keep in mind while designing the evaporator. Similarly, if you want to design a condenser, we need to make sure that it is going to reject the heat to the surroundings. It has to be appropriately sized for that. Again, the flow has to be such that the heat transfer is efficient, and the rejection is also fast. So for that, again, the surface area has to be proper. The fan speed, fan flow rate, CFM, the speed has to be proper, right? And there has to be adequate fins also. FPI also has to be proper. In case of condenser design, surface area also has to be proper. And the design of compressor, we need to make sure that it is sized properly depending upon what is the condenser pressure and what is the evaporator pressure. And this we do by using the pressure enthalpy chart which I had drawn earlier. Okay, so this is your pH chart and this is your compression process. Okay, so in compression process you have to match the cooling capacity, which is this. Okay, H1 minus H4. So this is 1 2 3 4. So H1 minus H4 is this. You have to match this. Then you have to take care of this pressure, that is condenser pressure, and the evaporator pressure, that will ultimately have a bearing on your compressor selection. This we are going to discuss in detail in our subsequent lectures. And the expansion device has to be such that it should prevent the flooding of evaporator. Flooding of evaporator means there should not be excess of liquid refrigerant in the evaporator, and also there has to be a sufficient superheat. What we mean by that is superheat means, this we are going to discuss again, but let me just hint at this what we mean by superheat. This is your saturation cycle, and this region is called as superheat. Okay, so this has to be maintained, this superheat has to be maintained while designing the expansion wall or capillary tube in your component sizing of the refrigerant. Okay, so these things you have to keep in mind while we talk about the design of refrigeration systems. uh, we will be talking about, as I said, about superheat. We'll be talking about what is the insulation which is to be there kept, how much it has to be kept there, which compressor has to be selected, how to select the fans, okay, and what should be the controls. All these things are important from the design angle. And then we need to be careful about other things like some control systems and sepsis systems, like there has to be a proper cutout in order to cut out switches which might cut down the or shut down the compressor if the pressure is too high. Okay, and there has to be a proper thermostat to maintain the temperature. There has to be a alarm system for proper control. Okay, and power monitoring system also, compressor selection, a production system has to be in place. So all these control and safety systems are also important in the design of your refrigeration systems. Okay. Um, to summarize, when we are talking about refrigeration system design, which will be an important topic and the core topic of our discussion in the course, a well designed refrigeration system would have an appropriate refrigeration capacity, evaporator capacity, the compressor would be correctly sized, the condenser would be correctly sized, correct capacity, and then we need to make sure that all these are correctly balanced, properly integrated so that there is no excessive frost happening, the consumption is not shooting up, and the temperatures are not unstable. Okay, so we need to have a well designed system. A systems approach is necessary when we talk about design of refrigeration system. Okay, so to summarize, as we are going to discuss in detail the design of our refrigeration systems, especially the design of blood bank refrigerators, freezers for vaccines or other cold chain things. This all the parameters, design principles have to be kept in mind, and accordingly, the if your fundamentals are clear, the design would be then better. Okay, with this note, I'll stop here. Thank you very much.